Okay, let's go ahead and get started then. So the goal of this lecture is to deliver the announced topic of the winter school, to tell you what a perfectoid space is, which means I need to tell you what a perfectoid ring is. Oh, it is recording, apparently.
Recording. How's the sound? I know. I want your feedback on the sound. It's okay? All right. Now you can have the screen.
Okay. So, again, the goal of this lecture is to get to the concept of a perfectoid space via the concept of a perfectoid ring and also a perfectoid Hooper pair. So, this will involve a lot of parallelism with the previous lecture. So Jared set things up very nicely for me. We'll take advantage of that to the fullest. So I'm mostly going to be thinking about a single Hooper pair. So this is and so this will be a Hooper ring, a ring of integral elements. So A, just like last time, has to be complete and analytic, but in fact, I'm going to be more restrictive on A for the purposes of exposition throughout much of the lecture. But we'll get to that in a moment. So we'll say that this pair, this is the basic definition. So we're trying to capture both what Jared talked about last hour and what Peter described in the very first lecture. So we will insist on a pair being for having the following conditions to be perfectoid. First of all, I want A to be uniform. Remember, that means that a circle is bounded. And for the purposes of writing down the rest of the definition, it's useful to note that because I'm working with something that's both analytic and uniform, means that whatever this A plus is, then it's also a ring of definition. Right? In general, that doesn't need to be the case, but in this case, I can take, A plus is open and bounded. It's open because it contains all the topologically nilpotent elements. It's bounded because it sits inside a circle, which is bounded. And it has a finitely generated ideal of definition because if I take some topologically nilpotent elements that generate the unit ideal, remember, analytic means that there are some topologically nilpotent elements which generate the unit ideal. Of course, you only need finitely many of them, and then if you take some large powers of them, then they get close enough to zero that they have to be captured in here. They're still topologically nilpotent. They still generate the unit ideal, so they give you an ideal of definition. But for the moment, if you want, you can just think of A plus being a circle. So if you're thinking about, for example, the case where A is a non-Archimedean field, maybe you want to think of A plus as being a circle. So I need an analog of the condition that Jared insisted on, that the evaluation not be discrete. Here I can say it this way. There exists, well, the combination of these two conditions will impose that. Try to make my letters more readable. So there exists an ideal of definition such that P is contained in the pth power of I. So this would, for example, rule out the case where A is QP and A plus is ZP, as we needed to do last time. And for some such ideal, the Frobenius map, or the p-powering map, which is because I assumed this, I get a well-defined homomorphism from A plus mod I to A plus mod I to the p, right? Because when I take pth powers of things, well, first of all, the pth powers of these things do get killed, and also if I have a sum of two things, then the cross terms are divisible by p, and p is in here. So this is a well-defined ring homomorphism, and I want that to be surjective. Okay, so I should maybe make a brief comment about how this looks, because there are various definitions of perfectoid rings at various levels of generality floating around. So the notes make some systematic effort to disentangle this. So this, for example, Peter talked about the case where you start with a perfectoid field. So first of all, so comments. Any perfectoid field, A, has this property. Well, a priori, you would take A plus to be a circle, but I should also make a comment that it turns out that this depends only on A, not on A plus, although it's actually not so obvious how to prove this directly from the definitions, but one thing I should say is that I'm going to state things in a certain order, and the way you actually kind of prove everything is a little game of Jenga where you have to stack things in exactly the right order, which is not the most natural order from the point of view of exposition. So the notes take care of that. So I will happily pretend that this order makes sense because it's the most natural one for explaining things. So this condition really is only a condition on A, as it turns out. It doesn't really matter which A plus you take. Any perfectoid field would give you an example of this. Right? If you think about, Jared showed that a perfectoid field has p divisible value group, so that allows you to choose a pseudo-uniformizer to take as the generator here that will have this condition, and then that works. Let's see, let me make some more room. So if we were in characteristic P, that's certainly allowed. So this is the comments continued. So if P equals 0 in A, then A being perfectoid is equivalent to A being uniform and perfect, well, and analytic, but I'm assuming analytic. So, for example, if you insist on having an example in mind that distinguishes analytic from Tate, you can kind of take the example that is in my notes from lecture 1 and sort of redo it, making everything perfect, and that will give you an example here. That's an exercise in the notes. I'm sorry? So the comment from Peter is that perfect is already enough to imply uniform. I think that's right. It's not obvious, so I'll sort of draw a so with some work you can show that if you're perfect, yeah, I guess you use the open mapping theorem somehow for this. So if you're perfect and analytic, then you're uniform, as it turns out. So let me dial back the level of generality somewhat from analytic to Tate. If A is Tate, it turns out you can always take I, the ideal that I used here, to be the principal ideal generated by some suitable pseudo-uniformizer. Again, it's not an entirely straightforward thing to go from this definition to saying that if there's some other ideal that works, then you can make one like this, but a posteriori, this all works out. Yes? Analytic means, for example, that the SPA has no points with trivial valuation, for example. Right, that was one of the ways that was characterized. So locally, an analytic thing is Tate. So for the purposes of constructing perfectoid spaces, it would be enough to consider Tate things. And also, I should, of course, point out something obvious. So, of course, I implicitly am taking the same prime P that Jared took in his lecture to be fixed, and everything in sight P is topologically nilpotent, of course, from the definition. So if A is a QP algebra, then, of course, P is a topologically nilpotent unit. So if you're interested in the case of perfectoid algebras which are QP algebras, then they are all automatically Tate. Of course, however, they're not necessarily all defined over a perfectoid field. Again, there's an exercise in the notes about that. So, for example, when I was initially doing this work with Liu, we were interested just in the cases of QP algebras, and so everything was naturally going to be Tate. I should just mention there do exist, so to speak, natural examples of perfectoid rings which are Tate but not QP algebras. But I think it is more natural if I leave that kind of example for next time, because we will actually use them in the next lecture. So for the moment, you might just want to think about the case where A is a QP algebra. But it turns out there are interesting examples that are Tate, but where P is not actually invertible. Well, of course there are examples, because there are characteristic P examples, but I guess the point I should make is that there are actually mixed characteristic examples, where P is neither 0 nor a unit. There are natural examples that we want to consider, but I propose that we pretend that those don't really exist for the moment. Checking for other questions. Okay, let me move on then. Okay, so time for some examples. Actually, before I do that, maybe I should mention another comment. So we'll see later that A being perfectoid implies that A is sheafy. That's not at all immediately obvious, but it will turn out to be true. So that means we can define perfectoid spaces as the adic spaces built out of pieces of the form SPA AA plus, where A is a perfectoid. So if an adic space can be built out of pieces, which are the adic spectra of perfectoid pairs, then we say it's a perfectoid space. Okay, and now with that definition, let me give some examples. Okay, so we've already seen the examples of perfectoid fields. So any perfectoid field is a perfectoid ring. So that gives us a starting point. So we've seen a couple of explicit examples from Jared's lecture. So for example, if you take the completion of the p to the infinity cyclotomic extension, or if you take an extension of QP obtained by joining all p power roots of p, some coherent sequence of those, you complete that. Those are both examples of perfectoid fields, so they also give you examples of perfectoid rings, which is useful because we can then bootstrap to create additional examples. Any algebraically closed non-Archimedean field of mixed characteristic, like CP, will again be perfectoid because the pth power roots condition is somehow trivially satisfied. There are many more examples that come from the old work of Fontaine-Vantin-Merget on fields of norms. So for example, if you take the completion of any, say, totally ramified and p-adic Lie extension, so if you take some Galois extension of, so say you start with a finite extension of QP, and you take some totally ramified extension whose Galois group is a p-adic Lie group, like ZP star, but it would also be like GLN, ZP. Then that turns out to give you a perfectoid field by combining the sort of original theorems of Fontaine-Vantin-Berger with an old theorem of Shankar-Sen. And so that gives you a large class of sub-extensions of CP, which are, again, perfectoid fields. So the perfectoid fields, one can get some handle on, and those give you lots of examples of perfectoid rings. But the whole point here is that there are lots of new examples from when you don't insist on things being fields. And I think the idea to try to get away from fields to more general rings, you first find this in the work of Faltings on p-adic comparison isomorphisms. So in particular, this example you would already find. Well, if you, say, took CP or something in this. So there are constructions that turn some perfectoid rings into other perfectoid rings. So you can start with a perfectoid field to bootstrap this. So if you start with a perfectoid ring, then there's something that I'm going to consistently write A angle brackets T minus P to the infinity. So this is the analog of the Tate algebra, but instead of putting in just T, I put in T and its roots. So if you want to see what this is explicitly, I can write it this way. So if I take A plus, take the polynomial ring in T, also adjoin P power roots, complete with respect to I, some ideal of definition of A plus. So this would give me the plus part of this, and then I have to tensor over A plus with A. So if I've done this right, that gives me what I want to call this. So I like to think a lot about rings with norms because I guess I'm used to that from classical functional analysis in the Archimedean case. So if A happens to have its topology defined by some norm, which can always be arranged, although it's the norm is more information. But if the topology on A is being given to you by some norm, then you're again taking some completion of the polynomials in A plus their p power roots with respect to the Gauss norm, the maximum absolute value of coefficients. But if you like algebraic notation, it would be this. So you have sort of a perfectoid version of the Tate algebra over some base perfectoid ring. And very often we do this also with the negative powers. So we have sort of the Laurent series, sort of the Laurent polynomial version of this. And of course, you can iterate this construction and do it with more variables. So if you are like me and you are reliant on the crutch of thinking about norms, if you have a norm on A, you can then talk about a weighted Gauss norm where it's the usual definition of a Gauss norm, except that T doesn't have absolute value 1. You prescribe its absolute value to be something else. The audio is getting out of whack there. So you can do an analogous thing with these perfectoid Tate rings. So that gives you an additional family. So for those of you who are used to thinking more about Berkovich spaces, you might be used to thinking about weighted Tate algebras, and so you have an analog of that construction if A comes with a norm. Okay, so those are some examples of perfectoid rings. Let me mention some naturally occurring examples of perfectoid spaces. So Peter mentioned one already. If, say, C is, well, let me call it K, actually. So say K is a perfectoid field, then if you take the analytification of projective space over K, and then you take the inverse limit with respect to the map that sends a point in homogeneous coordinates to the corresponding point where you take Pth powers everywhere, then if you take the inverse limit in a suitably defined sense, that would give you a perfectoid space. Concretely, what that means, if I pick an affinoid subspace here, then I get a family of affinoid spaces. So that, since that's a family of coverings on the level of spaces, it gives me a sequence on the family of rings where I can take the direct limit and then I take a suitable completion. So, for example, something like this, something like this, maybe I should say, or this. These things can arise in this way. So this is a general instance of a theme that you might identify, which is that general theme is that taking an inverse limit of, say, adic spaces, which, so to speak, should be inseparable in characteristic P, often leads to a perfectoid space. So what I mean here is that if K were actually of characteristic P, this map would, of course, be purely inseparable. So it's maybe not surprising that when you take this limit, you get a perfectoid space, because if you did this in characteristic P, you would clearly just be taking some sort of completed perfect closure. So it makes sense that taking this kind of inverse limit would give you a perfectoid space. And it's easy to modify this example by replacing Pn with your favorite toric variety. Because toric varieties are compactifications of tori. Tori, of course, have a multiplication by P map on them, which is sort of raising coordinates to the Pth power. So that extends to the toric boundary, and you can run the same sort of construction for one of those. And again, it's something that is, roughly speaking, lifting a Frobenius type thing out of characteristic P. Okay? So that's one kind of example. And this kind of example is already extremely useful. In some sense, when Rochuan and I were originally thinking about the circle of ideas that eventually merged with Peter's notion of perfectoid spaces, in some sense, we only really needed this kind of example because we were interested in sort of arguing that starting with some classical rigid space, you can make some cover that has sort of the convenient properties that perfectoid spaces turn out to have, and these were somehow all the ones we really needed. Well, this and on subspaces of Pn. But it turns out there are lots of other interesting examples that occur somehow in nature. So, for example, if you take the analytification of an elliptic curve, or more generally, an abelian variety, so over some perfectoid field, and this inverse limit is via multiplication by some say, well, let me just say some integer m, which is divisible by p. It could be p, but you could also have some prime to p stuff in there, or power of p, doesn't matter. This would again give you something perfectoid. So I don't remember whether this is one of the exercises anywhere, but this is a nice exercise. And again, it's sort of motivated by the idea that you're doing something, multiplying by p, and maybe some other stuff, that has a component in characteristic p, which is Frobenius. So it's sort of Frobenius plus possibly something else. And one other example that I won't say anything about in these lectures, but will be quite pivotal in Anna's lectures, is if you take a tower of modular curves, say over a perfectoid field, and you increase the level by, say, fixing the prime to p part and adding various powers of p. I suppose you could also add prime to p stuff in the level, but the key point is that you're increasing the power of p. When you do something like this again gives you a perfectoid space. And this somehow, the motivation is the same, but it's more subtle. It's the fact that, when you take a modular curve, so this is not, so to speak, a dynamical example, right? In these examples, I was iterating a single map. So here I'm not iterating a single map because the spaces are actually different. But it does have a similar flavor, and well, Anna will tell you more about this example later. And you can replace this thing also with Shimura varieties, but I think you have to read Anna's notes for that. Okay, so what do we know about these perfectoid rings or perfectoid spaces? Well, one of the important properties of them is that this whole story of tilting and untilting that Jared introduced in his previous lecture extends to perfectoid rings. So if I have a perfectoid pair, then I have an analog of the flat construction. So I can define A flat to be the inverse limit of A under the p power map as a multiplicative monoid. And inside that, I can take the corresponding inverse limit of A plus. I'll call that A flat plus, somewhat suggestively. So one of the key facts in this story is that the formula that Jared wrote down for addition continues to work at the level of rings. So if you have a sequence in this inverse limit and you index by n, so you have another sequence indexed by n as the result, where Zn is defined to be the limit as, say, m goes to infinity sorry about my infinity signs. So this is the same formula that we had in Jared's lecture. This equips A flat and, with a ring structure and let me write dot here so I don't write all the details in. The upshot of this is that A flat, comma A flat plus forms a perfectoid pair of characteristic P. So again, you use the same kind of argument that Jared explained to get a ring structure on A flat, and A flat plus will be preserved. You can again compare it to truncations. So maybe I should just mention the truncation, the analog of the truncation argument that Jared indicated in the. So note that the limit formula that I used to define A flat plus can be written equally well in terms of A flat mod I. Sorry, I don't need parentheses there. So these truncations have the property that these are actually ring maps. So this is manifestly a ring, and it turns out that the ring structure given here coincides with that one. And, well, there's a little bit more to say. I have to tell you how to put a topology on this, but there's a natural way to put the topology down somehow using, for example, if A has a norm, then you can use the projection map. Right, there's a projection map from A flat to A, which Jared called sharp, which I'll do likewise. So there's a projection map from A flat to A given by projecting a sequence onto the last component. And this likewise projects A flat plus onto A plus. So this will turn out to be continuous for the good choice of topology on here. So for example, if you have a norm on A, then you can sort of impose the norm on A flat by essentially saying that this map should be on isometry, and that will give you the right topology. And this is, again, multiplicative, like it was before. Because this original formula made sense on the level of multiplicative monoids. It was only the additive structure that I had to add in some other way, using the fact that P is topologically nilpotent, and taking Pth power somehow improves congruences in that context. So, I don't need to do that just yet. So let me not do that just yet. So again, following Jared's lecture, we can explain to what sense you can invert this functor. So this is a functor from so the tilting functor that goes from A plus to A flat plus from perfectoid pairs to perfectoid pairs of characteristic P. So it's not an equivalence. We already saw in Jared's lecture that if you took his two basic examples of perfectoid fields, they tilted to the same ring, the same field. So the way as this is written right now, this loses some information, but there is information that you can keep track of over here, which again, Jared talked about. So if you keep track of extra data on the characteristic P side, then you can make an equivalence. Of course, that data isn't strictly in characteristic P. It's some data to do with Witt vectors. So the data comes from the fact that, so if we take an element of the Witt vectors of A flat plus, then I can map that to A plus. Remember, a typical element of the Witt vectors in some sense, for the purposes of keeping track of what's going on, it's a good idea to think about Witt vectors as power series with coefficients in this ring, where the series variable is P. Now, that's, of course, nonsense, but it's useful nonsense from a kind of conceptual point of view. So if I have some element, so a typical element here will be a power series in P, where the coefficients are the Teichmuller elements lifting certain elements in characteristic P. So I like to write my characteristic P things with bars so I can keep track of which one is which. So the sharp map, I guess in my notes I like to write it sharp of xn rather than xn or sharp, but it doesn't really matter. So the sharp map tells you how Teichmuller elements, right? There's a multiplicative map from A flat plus to this ring, and there's a multiplicative map here, so it's natural to propose that this is how you should map these elements over here. And so one of the basic properties of Witt vectors, which may be worked out in one of the problem sets, I'm not actually sure, is that this kind of multiplicative map automatically gives you a map like this. And the other important point that it turns out is that this map is actually surjective. And this map also has a classic name. So this kind of map already appears in the work of Fontaine in the case where A is an algebraically closed perfectoid field. Fontaine called this map theta, and so we keep that terminology. And Fontaine already noticed in his context that this map is surjective, and he could say something about what the kernel is. And so those two statements will persist in this context. So the kernel of theta so it was generated by some element z, which these were called primitive of degree 1 by Fontaine. Although I should say, while Fontaine knew about this theta map for a long time, this notion of primitive element of degree 1, as far as I know, it came up only when he started working with Farg on the Farg-Fontaine curves. So, but that's still slightly before everybody knew what perfectoid things were. In any case, so let me remind you what primitive of degree 1 means, and since I'm going to say this a few times, I'll just call it primitive. There is a notion of primitive of degree 2, 3, etc., but I won't use it. So I'm going to write Z for a generic element of the Witt vectors that has a candidate to be a generator of the kernel. So the conditions are that the 0 coefficient here is topologically nilpotent, and that the 1 coefficient is a unit in A flat plus. So this condition is equivalent to saying that that if you take everything but Z0 bar and you group that together and divide out by the P, that this thing is a unit in the Witt vectors. So the way you're supposed to think about this definition, at least the way I would think about this definition, and it seems to work for me, so I do recommend it, is that remember, we're supposed to think about the Witt vectors as power series with coefficients in this characteristic P ring, and the series variable being P. So this is supposed to be like the analog of, if you want either a monic polynomial or a Weierstrass polynomial or Weierstrass power series. So this is like a monic polynomial in P, or better, a Weierstrass polynomial of degree 1. Right, and what I'm comparing to is, so this is a comparison with working a ring like ZP double brackets T, where you have an element like, say, T minus P to something. Right, so it's a monic polynomial. You have but you could multiply by a p-adic unit or even a unit in this ring, and that wouldn't really affect anything. You have a notion of Euclidean division for these things. T minus p to some power. Well, t minus basically anything divisible by p. Yeah, actually, that's true. I might as well write the t minus p times whatever. So t minus something which is not a unit would be a Weierstrass polynomial of degree 1, and you have a nice concept of Euclidean division for such things, because somehow this thing is a unit. You have a sort of a leading coefficient, which is a unit. But of course, yeah, you could multiply by some arbitrary unit in here, and then this would become a whole power series. So there wouldn't obviously be a leading coefficient, but you would still see that the linear coefficient is the first one that's a unit, and then that would behave like the leading coefficient. So this concept of a primitive element behaves very similarly to the concept of a Weierstrass polynomial, except now P is playing the role of the series variable. And so essentially, the derivations that you will find, for example, in the later part of lecture 2 in the notes, involve various calculations that are motivated by this analogy. So this is, in some sense, the way that you want to think about how these generators of the kernel look. Maybe I should make one or two other comments. So note. So any multiple of a primitive element by a unit is still primitive. So that it takes a little bit of work to check, but it's not difficult. But this is, again, what you expect from this analogy. So in particular, if you take some generator of the kernel, which is primitive, and you take any multiple of it by a unit, that would give you another generator, of course, and it would give you another primitive element. So in fact, what's really going on here is that the generators, the principal generators of this kernel are precisely the primitive elements in the kernel. So the content on top of this statement is that if I have another primitive element in the kernel, then it is a multiple of my original one by a unit. That's also not so hard to check. And again, that's sort of analogous to Weierstrass polynomials. So once you get the hang of this, then you can sort of go to town with building things out of characteristic P by quotienting by these things. So you can construct the inverse functor. So this is the version of this statement that actually includes the right data here and actually gives you an equivalence. So a flat. So if I go from a perfectoid pair here, but I keep track not only of the pair A flat plus, but also the kernel of the theta map. So this is an object of the category of triples R plus I where R plus is a perfectoid pair of characteristic P, and so this is an ideal of the Witt vectors of R plus, which is generated by some primitive element. So this is a long description, but so these things you can think of as forming a category, and you have a functor from here to here, and this is an equivalence. And the functor in the opposite direction is that if you give me a triple like this, then, well, two of the terms are easy to write down. I take W of R plus, sorry, one of the terms is easy to write down. So the A plus is going to be W of R plus mod I. So now to get this, I have to sort of invert something. So for example, if there's something, you have to invert something to get from the plus ring to the actual ring. So let me just say, let me not try to write, so the general formula for this is written in the notes. So one way to say this is, you can compute dot, dot, dot by taking what I call bounded Witt vectors over R. So you can take the Witt vectors with coefficients in R, just like you did in R plus, but there are too many of those. You want the ones where the coefficients of any particular element form a bounded set. And yes? That's correct. The short answer is no. Higher degree, the primitive elements of higher degree are not used in this construction. Yeah, I don't really want to say anything more about the higher degree primitive elements. There are things that correspond to Weierstrass polynomials of higher degree, but we don't really use them here. If I need to say something about them in a later lecture, I might do that. No, primitive elements of degree 1. Right, so, sorry, so I want this to really be like a monic thing. Okay, so if you want to figure out what goes here, well, in general, you have to take something between the Witt vectors of R plus and the full Witt vectors, and then just take the corresponding principal ideal there. If you restrict the left-hand side to perfectoid pairs with A being a QP algebra, then instead of this, you can invert P instead, and that would work. So, for example, if you read my paper with Liu, we invert P to form this thing. But as I said, next time I'll need some examples where P is not invertible, besides characteristic P ones. Right? Of course, as Jared mentioned, you can take the primitive element of degree 1 to be P itself, and then when you untilt, you just get back the same ring you started with in characteristic P. So that's included here. Okay. Great. Brian, can you remind me what time I'm supposed to wrap?
You've got 11 minutes.
Oh, it's more than I thought. Great. Okay. I'll listen for the crickets. So we have this equivalence, but this by itself would be, it would be useful. It was already useful for Fontaine.
Sorry.
Oh, okay. 2.5 minutes. Great. Okay. So I have less time than I thought. Great. I thought I had 5 minutes. So let me just then summarize. the many additional properties that are preserved by this construction. So, for example, one important one is that this construction is not only purely algebraic, which is what was known at the time of when Fontaine started working on this, but it also has a geometric component. The spas of these two pairs are actually canonically isomorphic, and this isomorphism is not just an isomorphism of topological spaces, but the rational subspaces on one side are exactly the same as the rational subspaces on the other. To say that it's a homeomorphism basically would be saying that rational subspaces on one side are finite unions of rational subspaces on the other. But this is even better. And this is related to the fact that the rational localizations on one side of this functor match up with the rational localizations on the other side, where you extend to this triple by just taking the kernel, by taking the ideal and just extending it to the target ring. So the fact that rationalizations coincide, that's saying that, well, a rational localization of a perfectoid thing is perfectoid. Well, since perfectoid things have to be uniform, that statement includes the fact that perfectoid things are stably uniform, which includes the fact that they're sheafy, which includes the fact that they're encyclic on rational subspaces. So this cascade of implications now falls out from the fact that it's easy to check that when you take something, a rational localization of a perfect thing in characteristic P, you stay perfect, and then you can transfer that information to the other side. And likewise, you have an analog of the compatibility with finite extensions that Jared talked about for perfectoid fields, that the categories of finite étale algebras over A and A flat match up. This statement doesn't really use the plus. So the finite étale algebras over A and A flat match up. So this reduces to the field case using crickets. So using the Henselian property of adic local rings for analytic spaces, which lets you sort of, so I'll just draw the picture of this and then maybe that's where I'll stop. So let me draw the picture here. So if you have So you have this space and this homeomorphic space down here, which is somehow a projection into characteristic P. We know that if you have some finite étale cover of this, that we can restrict it to points, and I get finite étale algebras over the corresponding field. So I have the equivalence for field, so I know that the sort of a cover of this corresponds to a cover of this point. And then the Henselian property lets me spread this out over some small disk, and then I glue things together. For example, you can use the fact that a finite étale algebra as underlying module is finite projective, so you have gluing for finite projective modules. You don't need to use that, but that's a conceptual way to do that. And this recovers, this implies the Falting's almost purity theorem, which is used in the construction of p-adic comparison isomorphisms. But in some sense, this is a much easier proof. And this is ultimately why I was thinking about this in the first place, because Falting's had this theorem whose proof I didn't understand. I think I had a similar experience to Peter. I couldn't really process the proof that Falting's gave, and so I was looking for something simpler, and Peter was also looking for something similar, and well, when a good idea, when its time has come, it sometimes comes more than once. So I'll leave that for now.
Okay, so I guess we have time for maybe a couple quick questions, and that's it. Questions?
There's one right over here.
Is it true that a perfectoid ring, as you defined it, is a perfectoid algebra for some perfectoid field?
No. In general, a perfectoid ring, even if you take a perfectoid ring over QP, say, it won't necessarily be a perfectoid algebra over a perfectoid field, because you can essentially write down a perfectoid algebra. You can give an example, which I do in one of the exercises in the notes, of a perfectoid ring which can specialize to both of the examples of perfectoid fields that Jared started with, and those have no common subfield. So that thing can't be a perfectoid algebra over any perfectoid field. However, in characteristic P, if you have a perfectoid ring which is Tate, then if you pick any pseudo-uniformizer, then that generates a power series field, and its completed perfect closure is also sitting inside, and that does give you a perfectoid field sitting underneath. So this is Jared's point about this being the sort of minimal example in characteristic P.
But you define it a perfectoid space as a spa of a perfectoid ring.
Locally, yes.
Yes, but as far as I understood, previous definition was for locally spa of perfectoid algebra.
Yeah, so Peter's original concept was you start with a perfectoid field, and everything is over that perfectoid field. And as you've seen, many of the natural examples occur that way, but the general definition doesn't require this.
One more question. Is it true that if we have a perfectoid ring which is a field, it will be a perfectoid field?
Yes, a perfectoid ring whose underlying ring is a field is a perfectoid field, but that's a non-trivial statement. That amounts to saying that the topology has to be generated by a multiplicative absolute value, and that's not obvious from definitions. There is a proof of it. The reference is in the notes, but it's a somewhat non-trivial statement.
Okay. One last question.
Can a Huber pair be perfectoid with respect to multiple different primes?
Can a Huber pair be perfectoid with respect to multiple different primes? I'm guessing the way I've set things up, the answer is probably no by some sort of open mapping theorem argument, because I'm assuming things are complete. If you were to weaken the hypotheses to somehow have some definition that doesn't require complete, then you could imagine taking something like Q bar and interpreting Q bar to be perfectoid sort of for all primes at once. But Peter apparently has a comment.
No, I mean, if a ring is perfectoid for some prime P, then P is topologically nilpotent in particular.
Yeah.
But if you have two different primes which are topologically nilpotent, then the ideal generated by them is also topologically nilpotent, which contains the identity,
Yeah.
and that's an issue.
Yeah, so because of completeness, you have a problem. But
Except the zero ring.
Yeah, but if you were to somehow define, you can try to make sense of defining a perfectoid ring without actually completing with respect to the ideal. You sort of say perfectoid with respect to P, meaning roughly speaking that the completion with respect to P, on some integral part, is perfectoid. So that you could have happen for more than one prime. As I said, if you take Q bar, you could sort of make sense of that. But we're not going to try to talk about that here.
Okay, let's thank Kiran again and go get...
$11:30.